Hello everyone, my name is Niki Lopi and my final project this summer was to visualize the aerodynamic model of submarine Spitfire. Visualizations are just the tip of the iceberg in CFD modeling. That is why today I'm going to go through all the three main stages of CFD simulations: pre-processing, actual simulation and post-processing. Pre-processing starts by obtaining a 3D model of the part. Then you need to apply some mesh generation tool to project the surface mesh on top of it. After that, you can create a volume mesh around the surface mesh. While creating a mesh, user needs to decide whether he implements unstructured or structured mesh. Unstructured mesh is easier to make, but structured mesh is more accurate and effective. The mesh has to be dense enough to acquire reasonable resolution, especially in the areas where large gradients occur. Furthermore, in the aerodynamic simulations, the size of the mesh has to be large enough so that the free stream boundary conditions can be defined for the mesh edges. Here you can see the 3D model of the airplane. Green and pretty. And here you can see the surface mesh, which is constructed from triangles. And here you can see the unstructured volume mesh created with ANSYS workbench. As you can see, the mesh is more dense near the airplane. In this stage, user has to decide the solver and the turbulence model. Commercial solvers can handle all kinds of simulations, but in OpenFOAM you have to decide which one is the most suitable. Before running the case, user has to define boundary conditions and discretization schemes. Typical trick is to start with more stable discretization schemes and then change them to more accurate ones when the simulation is already converged. Density-based steady-state solver raw porous MRF simple foam was chosen for this case because it can handle the rotating propeller. The turbulence model used in this case is the standard K epsilon, which is very robust since it uses wall functions instead of calculating the turbulence near the walls. OpenFOAM can handle multi-core run with decompose par utility. This case was run with 8 cores and 3000 iteration rounds took about 38 hours. After the simulation, you always have to remember to check the residuals to see if the solution is actually converged. And here you can see OpenFOAM running. It's actually not even this case, but still, look at it. It's amazing. In the bottom left corner, you can see the actual residuals for the Spitfire case. Post-processing can be done with various software. ParaView is used to visualize this particular case. In aerodynamics, the most important results are pressure distributions and velocity fields. Aerodynamic coefficients such as lift coefficient and drag coefficient can be calculated directly with OpenFOAM. Never trust CFD models without proper validation. Most of the problems result from turbulence modeling, and for example, the standard K epsilon model used in this case usually overestimates the turbulent viscosity and can't properly estimate the flow separation. Here you can see the pressure fields. Results seem to be reasonable: lower pressure on top of the wing and higher pressure on the bottom. Also notice that the high pressure areas near the leading edge are not in the same span-wise locations, since the propeller curves the airflow. And here is the flow field around the propeller. This is the average situation calculated with the moving reference frame. And finally here you can see the tip vortex, which is generated when the pressure differences try to level around the wingtip. In the era of supercomputers, it is cheaper to do simulations than, for example, wind tunnel and flight tests. CFD can handle most of the cases which are fully laminar or turbulent. However, problems occur when there's transition from laminar to turbulent or separation of the flow. There is a fixed velocity value of 80 meters per second in the inlet boundary, and for the outlet, the velocity boundary condition is inlet-outlet. The inlet-outlet boundary condition of open foam means that the velocity boundary switches from zero gradient to fixed value of zero if there's backflow. In addition, no slip condition is specified for every solid wall, and atmospheric pressure is fixed in the outlet. For example, you can run the case with different solver or turbulence model. However, definitely the best way to validate the simulation results is to acquire some real-life data, for example using wind tunnel or flight tests. OpenFOAM is open source software, so the main strength is that it is freely modifiable and user can learn more about the physics behind the simulations. And of course there's the fact that it is completely free. On the other hand, OpenFOAM is not that robust as commercial solvers and it is more difficult to use. During the summer, I got the whole picture of the simulation process. I learned how to work with large-scale 3D models, and I also learned how to decompose cases to multiple domains and run them in parallel. Okay, that's about it. Hopefully you learned something today, and you can send me more questions via email. Thank you.